So, um, yeah. So Austin did mention that, like, it would be kind of impractical to go all the way to 2010, but I think it's still beneficial for you to do at least the first few numbers of it, just to see like, just to establish like a sense of how the pattern is working. Right. Yes. But normally I like patterns like this. Sometimes it can be helpful to do the first patterns just to like establish like how the pattern is working to see more clearly. Okay.
Get so one thing that you think of, one mod that you might be thinking of working with here is mod 7, right? Because if we take this whole equation mod 7, the whole 7a term goes away, right? Because that's always going to be a multiple of 7. So then we get the equation is 11b is congruent to c mod 7, right? Because if we take the equation mod 7, the 7a term goes away since it's always a multiple of 7. And then with with this equation now, we can think about B mod 7 and what that would mean for C mod 7. So like if B was 1 mod 7, so I'm gonna say like if B was 1 mod 7, then that would mean C is congruent to 11 mod 7, right? Since one times 11 is just 11, and but then you can simplify 11 mod 7 to just being 4 mod 7, and then likewise you can do this with like if b is 2 mod 7, then C would be congruent to 22 mod 7, and 22 mod 7 would just be 1 mod 7. And then you can just keep listing this out for all of the potential mod 7s that B can be. Oh, B can also be 0 mod 7. So I don't know, I'll put this here, I guess. So B is 0 mod 7. Then C will also be 0 mod 7. Okay, and then so I'm just gonna list out like the numbers here. I'm not gonna put like all this again since it's like pretty repetitive. But B, if B is 3 mod 7, then C will be uh so it'll be 33. So C will be 5 mod 7. And then if B is 4 mod 7, then C will be um, C will be 2 mod 7. Is if B is 5 mod 7, then C will be 6 mod 7. I don't have to write the mod 7 here, but yeah. If B is 6 mod 7, then C will be 3 mod 7. Okay. Bill, are you good with everything so far?
Yeah. Uh, Shreya, do you understand like the concept of like mods and stuff?
Kind of, not really.
Okay. So mods, when Austin says something mod something, so like 2 mod 7, it means that he's saying that if you divide it by, oh, if you're dividing it by 7, then you have a remainder of 1. So that's what it means to be 1 mod 7.
So yeah, I think we should talk about um if she doesn't know mods, I think we should talk about like just mods like a little bit more.
Okay.
So I'm gonna make a new slide. So this is gonna be on the third slide.
Okay.
Okay, and then so we're just gonna talk about mods for now. So mods are basically just like the remainder function whenever you're taking division, right? It's like, if you're taking like division of like 10 divided by 7 or something, right? Like, you can say that this is equal to like 1 and 3/7, right? So like whenever you're doing division of this, you can think about it as like you can think about as you're getting 1 and then a remainder of 3, right? Whenever you're doing mods, it's like division, and you're getting the remainder of the division. So if I were gonna think about like mods, it would be you would be saying um, 10 mod 7. And then 10 mod 7, this is like if you're doing the division 10 divided by 7, what remainder would I get? You would be getting a remainder of 3, right? Um, so then 10 mod 7 would be equal to 3. You can see that this is congruent to 3 mod 7. But basically, I don't know. For now, you can just think of like 10 mod 7 is equal to 3 because if you divide 10 by 7, you have a remainder of 3. So does that make sense so far?
Yes, that makes
Okay.
sense.
Um, and Bill, are you good with that so far?
Yeah.
Okay. Um, so yeah, so basically um, like I was talking about before, if you're working with equations that just involve integers, they're called Diophantine equations, but I mean, I don't know, the name doesn't really matter. So do you know like what integers are?
Yes, I do.
Yeah, okay. So yeah, basically, if you're working with equations involving just integers, um, a lot of the times, or like you want to keep in mind of like working the equation like with mods because like it can reveal a lot about the equation and it can like lead you to like getting more properties of the equation essentially. So um So like our original equation here was 7a plus 11b, and it's equal to c. So all these a, b, and c are all integers. So what we were doing here is we were taking the whole equation mod 7. So we're thinking about the whole equation as if you divided like the whole equation by 7, and you're thinking about what remainder that would be. Also, like mods are distributive. So like if you're taking like let's say 8 plus 2 mod 7, you can say that this is equal to 8 mod 7 plus 2 mod 7, right? And then 8 mod 7, if you think about the remainder of 8 divided by 7, that's just going to be 1, right? So then, you can say that this is equal to 1 mod 7 plus 2 mod 7, right? And essentially you can combine this back up again like this, 1 plus 2 mod 7, and then this is just equal to 3 mod 7. And then, you can see that what we started with, it was just 10 mod 7, right? And then you can see that, if we distribute, we still get 3 mod 7. And before, just by doing it, we also got 3 mod 7. And then, when I say 3 here, it's technically, there's like a mod 7 behind it. So like, whenever you're working with mods, there's not really like an equals to. You're always talking about like congruent to. So like what I'm saying here, when I'm saying 10 mod 7, I'm gonna say like 10 mod 7 is congruent to 3 mod 7. And what this is saying is it's saying 10 divided by 7 has the same remainder as 3 divided by 7. Um, and yeah, but like usually you want to think about the mods in like the least number. I don't know, like you want to I don't know. Wait, first, Bill, is there anything you want to say so far?
No, I'm good.
Okay. Um, yeah, so when we're saying 10 mod 7 is congruent to 3 mod 7. So we're saying that like 10 divided by 7 um has the same remainder as 3 divided by 7. But usually like if we're given like 10 mod 7, usually you want to reduce this to to the number that you I I don't know. Can you help me out, Bill? I'm having trouble. I don't know.
Wait, what are you having trouble with?
I don't know. I guess this is like a little bit weird. I don't know. For now, I guess you can just think of like for now you can just think of like the mod function just being like a remainder function. So just I think just thinking about like 10
Yes.
mod 7 is equal to 3 mod 7, if that's okay. Um, so do you think you're good with that so far? Is there anything that's unclear?
No, I understand it.
Okay. Um, okay, so let's try to apply this into the equation. So okay, I'm making a new slide. Okay, so we have 7a plus 11b is equal to c. So we're thinking about this equation in mod 7. So you can think about it like this, in mod 7. So yeah, so the mod function is distributive. So um we can like distribute this mod 7 to like every term of the equation. You can think about it like that. So you can think about like if we're thinking about the equation in mod 7, it's like we're thinking about 7a mod 7 plus 11b mod 7 is going to be equal to c mod 7. And like, anytime you have an equation with like integers, I guess, you can just you can always do this, like just apply mods to everything, and then you turn it into a new equation with just mods. And you can do the mod with like any integer that you want. So you can do mod 8, mod 9, mod 10, and so on. But we're choosing to do mod 7 here. So why are we choosing to do mod 7 here? Well, if you look at this term, 7a mod 7, yeah, 7a mod 7, oops. 7a mod 7, so a is an integer, right? Which means that 7 times a is always going to be a multiple of 7, right? So if 7a is always a multiple of 7, then do you see that like 7a mod 7 would always be equal to 0 because 7a is always a multiple of 7. And then if you have a multiple of 7 divided by 7, you're always going to have a remainder of 0. So, so yeah, so 7a mod 7 would always be equal to 0. And then the 0 really helps in the equation, right? Because if you make something 0, then you have less terms of the equation to work with. So that's why we chose to do to take the equation into mod 7. You can also choose to take the equation into mod 11, right? Because if you take the equation in mod 11, then you can get rid of the 11b term, right? Like with the same reasoning as before, 11b would always be a multiple of 11. So then 11b mod 11 would be equal to 0, and then that takes away a term from our equation, which makes it simpler, right? So you can choose to do either one, but mod 7 is probably a little bit simpler because like the smaller the mod number that you're working with, usually the equation is going to be a little bit simpler. But yeah, so does that make sense so far?
Yes, that makes sense.
Okay. So yeah, so if we take this equation into mod 7, the 7a mod 7 term will go to 0. And then what we have is just 11b mod 7 is equal to c mod 7. And then from this, we can, well, we can also reduce the 11 into 4. So we can say that um, we can reduce this equation from 11b mod 7 is equal to c mod 7 into 4b mod 7 is equal to c mod 7. Um, so what we did there is we took 11 minus 7. Um, so um, basically, if you have like anything like multiplying by each other, so we have like 11 times b here, right? If we have anything that's multiplying by each other and we're taking it all like a mod 7 in this case, we can also choose to take the mods of the individual components. So what I did here was I took the mod 7 of 11, and mod 7 of 11 is going to be 4, right? Um, so yeah, basically I reduced the 11 down into 4 because I can also just take the mod 7 of anything that's being multiplied by each other. Um, and so if I reduce 11 down into 4, it makes the equation like a little bit easier to work with. But you can also just work with the original 11b mod 7 is equal to c mod 7 if you wanted to. Okay. So yeah, so now what we've done is we've made like a new equation from our previous equation by taking a mod 7, right? And now we can get like more information about the relationship uh about B and C using this new equation that we have. So so what I was doing earlier was I was thinking about um the possibilities of what B mod 7 would be and what that would make C mod 7 have to be. So I was starting out with like if B was equal to 0 mod 7, what would C mod 7 have to be? Well, C mod 7 would have to be 0 mod 7, right? Because if B was 0 mod 7, the 4B term would be 0. And then you're taking, and then, the 4B term would be 0. And then you have 0 mod 7 is equal to C mod 7. And then this is basically just telling you that C is equal to 0 mod 7. Um, you can also think about this as like, if something is 0 mod 7, you're saying that it's a multiple of 7. And then, if B is a multiple of 7, and then you're multiplying it by 4, it's still going to be a multiple of 7. And then you're taking a mod 7, that's going to be 0. So C would also have to be 0 mod 7. So what I'm saying here is that if B is 0 mod 7, C would also have to be 0 mod 7. So does just that part make sense so far? Um,
Um, yeah, sorry. Yeah, I'm good with this.
okay,
So,
and anything you want to add so far, Bill?
Um, not really. I think.
Okay. Uh, okay. So yeah, we can continue this line of like if B was this mod 7, what would C mod 7 be? So we can think about if B was 1 mod 7, what would C mod 7 have to be? And basically, if B was 1 mod 7, then 4B, 4 times B, we can just think of, because we're working everything with mod 7, we can just think of B being equal to 1. And then B being equal to 1, we can just multiply it by 4. And then, 4 times B would just be 4, right? And then our equation would be 4 mod 7 is equal to C mod 7. So then this is saying that C is equal to 4 mod 7, right? So it's telling us that if B was 1 mod 7, C would have to be 4 mod 7. So does that part also make sense?
yeah.
Okay. So then we can just continue this for every possible B mod 7 that there could be. So we can continue it on for B is 2 mod 7. We can think about 4 times B, it would be 8, right? So C is congruent to 8 mod 7. But we also want to reduce the 8 to the like lowest number that we can. So 8 mod 7, we could reduce that to 1 mod 7, right? Because 8 divided by 7, that would give you a remainder of 1, right? So then this is saying that if B was 2 mod 7, C would be 1 mod 7. Okay. So yeah, if B was 2 mod 7, C would be 1 mod 7. Okay, so now if B was 3 mod 7, we would have 12 mod 7 is equal to C mod 7. And then we could reduce the 12 mod 7 into 5 mod 7, right? Since 12 divided by 7 has a remainder of 5. And then, that's saying that if B was 3 mod 7, then C would just be 5 mod 7, right? So we can continue doing that for each of these. So basically we're figuring out um, each mod 7 of the B, what that would correspond to what mod 7 the C would have to be. Okay, so B was 4 mod 7. Then, we would have 16 mod 7 on this side. And then 16 mod 7 would just be 2 mod 7, right? But whoops, since um, since 16 divided by 7 has a remainder of 2. So yeah, so B is equal to that would mean C would also have to be equal to 2 mod 7. And then if B was equal to 5 mod 7, then we would have 20 on the left side, and then 20 mod 7 would be 6, right? Since 20 divided by 7 is equal or has a remainder of 6. You can also think about like the nearest, the highest multiple of 7 that goes that is below 20 would be 14, right? And then 14 is 6 away from 20. So that's another way you can think about how mod works. So yeah, if B was 5 mod 7, then C would be equal to 6 mod 7. And then lastly, we have B is equal to 6 mod 7. If B was equal to 6 mod 7, then we have 24 on the left side, and then 24 mod 7 would be 3, right? So then C would have to be 3 mod 7. And then that's all the mod 7s of B that we have to consider, right? Because, if we go on, if we say B is equal to 7 mod 7, well, 7 mod 7 would just be 7 mod 7 is the same thing as saying B is 0 mod 7, right? Because 7 mod 7 and 0 mod 7 are the same, right? Because 7 mod 7 is 0 mod 7, right? Because 7 divided by 7 has a remainder of 0. So basically, we don't have to talk about B is 7 mod 7 because we've already talked about it whenever we talked about B is 0 mod 7, right? And you can also see that if we apply B is equal to 7 mod 7 into the equation, you get the same thing as before with C. C is equal to 0 mod 7 because because if we put in 7 as B, we'd have 28 on the left side, and then 28 mod 7 is just 0, right? So then C is 0 mod 7. So we can see that it gives us the same thing if B were 7 mod 7 as if B were 0 mod 7. And that makes sense because 7 mod 7 and 0 mod 7 are the same thing, right? And then, if we were to do B is 8 mod 7, we also don't need to do that because 8 mod 7 is the same thing as 1 mod 7, right? Because 8 divided by 7 has a remainder of 1. And so if we look at what B is 8 mod 7 is, it's just going to be the same thing as if B 7. So we don't have to if B were 1 mod 7, right? And then likewise with all of this, we don't have to think about any higher mods of B, right? Because any higher mods of B, it will always reduce down to a lower mod that we've already talked about. So does that make sense so far?
Yeah. Mm.
Okay. Um, so now let me see here. Okay. Okay, so we want to think about the original equation again. So 7a plus 11b is equal to c. So, a and b are integers, and we're looking from what integer 7a. First, we can think about if b was 0 mod 7. So if b was 0 mod 7, c would also have to be 0 mod 7, right? Now, if c, we can think about it like this. If c was 0 mod 7, we can always get whatever c is, right? Because we have a 7a term in our equation. If c was 0 mod 7 or c was a multiple of 7, we can always um, we can always make it a possible value of our equation by just having 7a equal to c, right? Does that make sense? So like if c was a multiple of 7, we can always have a solution for it, because just by having b is equal to 0 and then 7a being equal to c, and then c is a multiple of 7, so we just have a to be whatever c divided by 7 is, right? So essentially, if c was 0 mod 7, we will always have a solution for it. So that tells us a lot about the equation, right? It tells us that we can always get a multiple of 7, any multiple of 7 that we want to. So yeah, so we can say that I'm gonna need another slide for this. So I'm gonna make a new slide. So I'm gonna work on the fifth slide now. So yeah, so 7a plus 11b is equal to c. If c was 0 mod 7, we can essentially get we can get any of it. We can get any solution for c if c were 0 mod 7. Okay. So now what if so we can continue down our mod 7 path that we made before, right? So, if you want to look back to it, you could just look back to it on the previous slide that I made, right? So now we're going to look at the second line. We're going to look at b. If b is 1 mod 7, that would mean c is 4 mod 7, right? So if b was 1 mod 7, if b was 1 mod 7, c would have to be 4 mod 7, right? We've already established that. But if b was 1 mod 7, the minimum value of 11b would have to be 11, right? So like if you think about if b is 1 mod 7, think about what values b can be, right? B can be equal to 1, right? Because 1 1 divided by 7 just has a remainder of 1, right? So b can be equal to 1. But what else can b be equal to? Well, it can be equal to 8, right? 8 divided by 7 has a remainder of 1. And then it can also have, or sorry, b can also be equal to 15, right? 15 divided by 7 also has a remainder of 1. And then you can just keep thinking about this as like you're adding 7 to each of these, right? So b can be also 15 plus 7, which is 22, right? 22 divided by 7 also has a remainder of 1. Like as you see here, the only possible values of b you can have is just going to be a 1 or greater, right? You can have like infinite values of b, but they're all going to have to be greater than 1, right? You can't have b being less than 1 because b is a positive integer, right? As noted in the problem, right? So the minimum value of b would have to be 1, right? So that means that the minimum value of 11b is 11, right? And then if if we're taking b to be equal to 1, then we can get any solution for c is equal to 4 mod 7, right? Because, if you think about, if we had c is equal to 4 mod 7, if c is equal to 4 mod 7, if c is equal to 4 mod 7 and b is equal to 1, that means our equation, 11b would just be 11, right? And then, we can move the 11 to the other side. We can say 7a is equal to c minus 11. So if c is 4 mod 7, then c minus 11 would always be a multiple of 7, right? And then if c minus 11 is always a multiple of 7, that means we can always get a solution for it from a 7a, right? Because a is an integer, a can be, or like a is a positive integer, and it can be any positive integer that we want it to be. And then we just equate it so that we have a solution for c, right? So so let's think about like a possible value if for c, if c was 4 mod 7, like c could be equal to something like, whoops, c could be equal to something like 25, right? If c was equal to 25, c is 4 mod 7, right? And then if c was equal to 25, we'd have 7a is equal to 25 minus 11, and then 7a is equal to 14, right? And then 14 is a multiple of 7, right? So then we could just find an a so that um, 7 times a is equal to our multiple of 7, 14, right? So then in this case, we can just say a is equal to 2. So basically, with any c that is 4 mod 7, we can always get a solution for it for a um, because the 4 mod 7, whatever it is, minus 11, it will always be 0 mod 7, right? Because 11 itself is 4 mod 7. So whenever you have something 4 mod 7 minus another 4 mod 7, will always give you 0 mod 7. But there's one exception here, right? Because a cannot be, or a has to be a non-negative integer. A cannot be negative, right? So the only c that is 4 mod 7 that cannot work is 4, right? If c was equal to 4, then this side we have 4 minus 11, and then you see that, on the right side it's still 0 mod 11 or 0 mod 7, right? And by the way, you can still take negative integers mod something. If you have negative integers mod something, it's like you're doing the same thing essentially as if there was no negative. Um, but then, you can add it to whatever mod you're working with. So like here, another way of thinking of mods. So like if we have 10 mod 7, um, another way you can think of it is I can add 7 or take away 7 to the 10 as much as I want. So I can say 10 mod 7 is equal to 10 plus 7 mod 7, right? So I can say 10 mod 7 is equal to 17 mod 7. And that's true, right? 10 divided by 7 has the same remainder as 17 divided by 7. And then, I can also take away 7 from 10, and then it's saying, 10 mod 7 is just 3 mod 7. And that's also true. But you can still take away a 7 from the 3. And then if you take away the 7 from the 3, then it becomes negative 4, right? So then you can still say that 3 mod 7 is congruent to or equal to negative 4 mod 7, right? So basically, if you're ever doing mods with negative integers, so like if you're doing negative 11 mod 7, um, you could first think about taking, if I was just doing 11, remainder of 11 divided by 7, which is 4, right? So I could say that negative 11 mod 7 is equal to negative 4 mod 7. But then I can think about adding a 7 to the negative 4. So I can say negative 4 mod 7 is congruent to 3 mod 7. That's not a negative there. I just accidentally wrote. But yeah, so that's how you can convert like a negative mod something into a positive mod something. But basically, like, you can also work with mods with negative integers. But yeah, but all I'm saying here is that like negative 7 is mod 7 is still 0 mod 7. Okay, but anyway, so what we were doing here is we were thinking if C was 4 mod 7, can we get all the C's? We've shown that we can get like most of the C's, because if C is 4 mod 7, like I said, C minus 11 would be 0 mod 7, and then you can just make A whatever you want it to be, so that a 7A equals whatever that multiple of 7 is. But the exception here is that A has to be a non-negative integer. A cannot be negative, because if you think about the original problem, we're erasing numbers that are 7 or 11 more than a number that we've already erased. But you can't erase a number that is 7 less or 11 less than a number you have already erased, right? So that means your A and B can't be negative. So if A can't be negative, then you could see that, if our right side was negative 7, then we would have no solution, right? Because our solution would have to be A is that we don't have a solution here. So, but if C is anything else for mod 7, you would have a solution, right? Like, let's say C is the next mod for mod 7. If C was equal to 11, if C was equal to 11, then the right side would be 0. And then we have 7A is equal to 0. And then we would just have A is equal to 0. Because and this would work because A can be 0. It just has to be not negative, right? Okay, so our whole conclusion for just this part is we're saying that if C is 4 mod 7, um, if C is 4 mod 7, we can get any except for C is equal to 4. So we can get any of this as long as C is greater than 4. We could say that. So whenever we're looking at C is equal to 0 mod 7, um, we could get any possible value of C, assuming that C is a positive integer or a non-negative integer, which it is. And then we were looking at if C is 4 mod 7, we would always have a solution for it as long as C is greater than 4. And we can apply this for each of the mods. And essentially, if we apply this for each of the mods, we'll see that like it's going to be the same thing. It's going to be like we'll always have a solution for C as long as C is greater than this sum amount. And 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 then like as long as C is greater than the sum amount, well, the essentially it gives like a minimum for all the C's in that mod 7 range, right? And then from all of the mod 7s, you want to look for the the largest the largest the largest minimum that the C cannot be. And then the largest C that there cannot be, well, that's going to be our answer. Well, also +1 because we neglected the +1 from earlier. Okay. Say so far, Bill, or also does that make sense so far?
Well, the making sense should be like, yeah, I mean, it makes sense to me. What about,
Oh, okay. Well, do you have anything to say so far?
uh,
Um,
go ahead.
sorry. Uh, sorry. I thought you were asking me about that. Never mind. I'm sorry.
Oh no, go ahead. Did you have your, do you have anything you don't understand? Do you understand all this?
Yeah, it's making sense.
Okay. I personally don't have anything to add.
Okay. Um, okay. Also, do
Hmm?
you want to keep on working this, or I can also keep on working on this? What do you
Uh,
think?
you should finish it. I don't think
Okay.
I don't think I actually solved this problem. So,
Okay. Okay. I can finish it. Um, okay. So, we finished looking at um we finished looking at another combination of, what B and C mod 7 were. And now we had to continue with the next mod 7 of B and C. So we're gonna now look at B is 2 mod 7 and C is 1 mod 7, like said in the previous slide. So I'm just gonna say, like, if C is 1 mod 7, so if C is 1 mod 7, um, we're saying that B has to be 2 mod 7, right? That was said in the previous slide. So if B is 2 mod 7, then like the possible values B can be would be like 2, 9, and then etc. Right? You can just add 7 to B. But basically B would have to be something that is 2 or greater, right? So then the minimum value of 11B in this case would be 22, right? So the minimum of 11B would be 22. And then basically C would have to be uh oh wait,
wait,
hold on.
what?
Yeah,
What
did you
has
see
this?
that?
Yeah, what has this in a thing?
It might wait,
This has never been
it
a
might
thing
be like a
before.
new feature. It might be a new feature. Well, not a feature, but
What?
wait, wait, so we see a thing here that says
Your
your
call.
call ends in 5 minutes,
Uh,
like on the Google Meet.
we could always just leave and rejoin.
When was this a thing? This has never been a thing,
Yeah, I don't.
right?
I've never remembered this being a thing.
Okay, well, so I suppose in 5 minutes we'll have to leave and then rejoin the call, I guess. Like we did in Zoom before.
Oh, it
Anyway.
started 6 days ago or something. Apparently.
Oh, interesting.
Okay.
Okay. I'll make sure to rejoin
Okay.
after it ends.
Okay. Okay, so yeah. So we're working with C is 1 mod 7, so B has to be 2 mod 7. So the minimum of B would be 2. So then the minimum of 11B would be 22, right? So then C has to be 22 or greater, right? C has to be 22 or greater. If C was less than 22, then the C minus 11B. If C was less than 22, C minus 11B would always be negative, right? Because we just said that 11B, the minimum value is 22, right? So C was less than 22. C minus 11B would always be negative. And then, if C is minus 11B is always negative, then there's no solution for that C, right? Because A cannot be negative. 7A cannot equal a negative number, right? So that means that C has to be greater than or equal to 22. But then does every C that is greater than or equal to 22, can we always get a solution for that? Well, actually, yes, because then we can always just say whatever C is, we can just have B being equal to exactly 2. And then we would just always have C minus 22. And then if C is greater than or equal to 22, then C minus 22 would be positive or non-negative, my bad. And then if C minus 22 is non-negative, we're also saying that C is 1 mod 7. Well, B, or sorry, 22 is also 1 mod 7. So then C minus 22 would always be 0 mod 7. And then, and then because it's also always non-negative, then we also always have a solution for it for whatever corresponding A it corresponds to, right? So then we're saying here that um, if C is 1 mod 7, um, we can get any solution for it as long as C is greater than or equal to 22. And the previous one, I should probably say it's greater than or equal to 11. I think that might make a little bit more sense, but I mean, ultimately, I guess it doesn't really matter. Okay, so we want to continue with the next C mod 7. So C is 5 mod 7. So if C is 5 mod 7, then B would be 3 mod 7. So if B is 3 mod 7, um, if B is 3 mod 7, then B can be 3 or 10 and so on, right? But the minimum B can be would be 3, right? And so the minimum 11B can be would be 33. And then this is like the exact same thing that we said before, right? With the C is 1 mod 7. Essentially, C has to be greater than or equal to 33. Um, but as long as C is greater than or equal to 33 and it's 5 mod 7, then we can also always get a solution for it for its corresponding A. So this will also be any Oh, you put it on the gym. Uh, hey, how do you wanna like work in the problem? Okay, so yeah, sorry for that inconvenience. We didn't know that would happen, but um, I guess we'll try to find a workaround for future meetings.
Mm.
But okay, so let's return to the problem, and yeah, so we're talking about if C was 5 mod 7, like before, um, the minimum of B would be 3, so the minimum of 11B would be 33. So then C would have to be greater than or equal to 33. And as long as C is greater than or equal to 33 and C is 5 mod 7, then there will always be a solution for C. So that's just done with like the same reasoning that we did for when C was 1 mod 7. So yeah, C is greater than or equal to 33. Um, okay, so yeah, so let me erase this. So, so yeah, we can do this for each of the C's. So we can move on to like if C was 2 mod 7, if C is 2 mod 7, then the minimum of B would be, or so if C was 2 mod 7, B would be 4 mod 7. So then the minimum of B would be 4. So then minimum of 11B would be 44. So then with the same reasoning as before, C would have to be, C would have to be greater than or equal to 44. And then maybe see kind of a pattern now. Whatever C mod 7 is, we will have any solution for it, but C will have to be greater than or equal to um, whatever B mod is times 11. So in this case, if C is 6 mod 7, we can have it any, but it has to be greater than or equal to 55. And then with the last case, if C is equal to 3 mod 7, then we would have a solution for it, but C would have to be greater than or equal to 66. Okay, now we have a full census of what solutions of C that we can get, right? Essentially, for any C, you will have a solution for it, but you will have to check in that particular whatever C mod 7 is, you have to check if C is above that minimum value, right? Um, so our original problem here was what is the largest number of C plus 1 that we cannot have a solution for, right? So if you think about this, well, the largest C that we cannot have, the largest C plus one that we cannot have a solution for it's gonna have to be on this row, right? It's gonna have to be C is equal to 3 mod 7, right? Because in this case, C has the highest minimum value, right? So if C has the highest minimum value, that means it's gonna have the highest maximum value that we cannot get, right? So then what is this highest maximum value of C that we cannot get? Well, we can get C is equal to 66 in anything that is above that, but we cannot get the C that is below that, right? But that is also 3 mod 7, right? So then what is the C that is um, 3 mod 7 that is directly below 66? Well, it would be 66 minus 7, right? Because 66 is already 3 mod 7. So then we just take 66 minus 7, which is equal to 59. So essentially, um, 59 is the largest 3 mod 7 that is below 66. So 59 would be the largest value of C that we do not have a solution for, right? So then, and remember, C was not our actual set of numbers, right? Our actual set of numbers is going to be C plus 1 because we removed the plus 1 before. So that means if we move all of this up by 1, that means the largest number that we do not have a solution for is going to be 59 plus 1, or 60. And I can pull up the answer here for a 2010 team. And yeah, the answer for number 8 is going to be 60. Okay. So yeah, so just for this one problem, that seems like a lot of work. And essentially, essentially for each of these team problems, you only have like technically like 8 minutes to work on it, but technically actually like less because it's like less time for more people. But anyway, so like the question is like how are you supposed to do this like quickly? Well, um this is a pretty tough problem. But it's just like if you're like more fluent with like working with mods and stuff, then you can get by with doing these mods and stuff like a bit faster, and you don't have to like actually like list out like everything like how it did. So like when I was working through this, like on here, I listed out like what every B mod 7 is and what every C mod 7 would be, right? But like if you're really fluent with working with mods, all you would know that um the 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 solution for like the maximum number that you cannot get, it would have to be in the largest mod 7 of B, or B is 6 mod 7. And then you just find what C mod 7 in that case of B mod 7, B is 6 mod 7 is, and then you get to the solution pretty fast. So basically, for this problem, you do have to be pretty fluent with working with mods to get it quickly. But you know, if you're not, just being able to work through this problem and understand this problem is it's good with like practicing working with mods, I guess. Okay. Anything you want to say for that question, Bill?
Right. So, since you're kind of new to mods, this whole thing might seem a bit like daunting. But mods is the concept, modules, I think.
Modular arithmetic?
No, just like mods. Uh,
What?
whatever. But yeah, like mods is something you'll see a lot more once you start getting into like competitive math and stuff, like math Olympiads and stuff. And yeah, in time very familiar with the concept.
Okay.
Okay. And do you have any questions for us for this question?
No, not really.
Okay. Um, okay, we
Well,
can move on to the next question.
we spent a lot of time on that.
Well, yeah, well,
Okay.
yeah, I mean, if you're not fluent with mods, that question would take like pretty long. Yeah.
Okay.
Um, but like it's like if we're starting with mods, like it's good if you can understand the method that we used. Okay, but let's move on to the next question. It's gonna be number 9. Um, the flower of life figure is shown. The smaller circles have a common radius length of 16 units each, and the large circle has a radius of 18 units. What percent of the large circle's area is not included in any of the smaller circles? Express your answer to the nearest whole number. Okay, so
Do you want me to do this one?
yeah, sure.
Okay. So do you want me to do your method or my method?
Um, I mean, you could show both, right?
Okay.
I mean, you
So
can show how like there's a lot of methods.
okay. So first of all, do you know how to? Do you know like area of a circle and stuff?
Uh, yes, I do.
Okay, good. So So let's look at the problem first. It's saying we're looking for the percent of the large circle's area that is not included in any of the smaller circles. So the smaller circles will be like these smaller circles. So the area we're looking for will be like these parts. So like these parts are the ones not included in the small circle. So when we have something like this, we want to be able to express it in terms of like areas that we can find because this area obviously we don't know like how it is, but we could express it in something like this. So let's say we just look at this one. We just look at this part of it. So if we draw lines here to the center of the circle like this,
To the center of the big circle.
yeah, the center of the big circle. Actually, we get a different color for a big circle.
So wait, so do you understand like what area we're trying to find in this figure first?
Uh, yes, I think so.
Yeah, so it's just like it's like this outside area. It's included in the big circle, but not any of the smaller circles. And you have like 6 sections of it, right? It's like,
Yeah.
yeah, okay, yeah. So we're trying to figure that out.
Okay, so if we were to just look at this part of the pie, like this part of the circle, whoops. So this is like 1/6 of the circle, right? Does that make sense? How this part is like 1/6 of the circle? How this whole part
Like
is
the
like,
whole, like if you look at if you look at a black pen, like that whole like circular sector is what it's called. That should be that should be 1/6 of the area of the largest circle. Do you see that?
Um, yeah.
okay. So we know, so this area, we can find this area, right? So this is the area we can find. And also, this triangle right here, this triangle, the equilateral triangle here, we know that it has side length 18. So we know the side length, and we know that it's equilateral because this is
Well,
60.
yeah, sorry, you can get the side length from knowing that the radius of the large circle is 18, right?
Yes. So
Yeah.
because it's 18 and we know it's equilateral because this will be 60 degrees, the triangle has an area we can find. So we know the area of this part.
Wait, what was your explanation of knowing that it's equilateral?
So it is a sixth of the circle, right?
Yeah.
So because of the sixth of the circle, this angle right here will have to be 60 degrees.
Yeah.
And if this is 60 degrees, and these two sides are congruent because these both are radiuses of the circle, so they're both 18.
Yeah, then it would have to
So
be,
both of these would have to be 60 degrees.
yeah.
Yeah,
You can also see that just from like if you look like if you just like count all the sides,
right,
like you see that it's they're all equal length, right?
right,
So
yes.
yeah, you can figure out that it's an equilateral
Okay.
triangle.
So now we know that this area is the area that we can find. This area right here. So to find the area we're looking for, we just have to subtract these smaller petals, right? Like these parts. And these parts are also parts you can find because like now I can get rid of this.
Right. You should also make clear that like we're looking at like half of the petals on each of those, right?
Right.
Um,
So we're looking at this part right here.
like the triangle that we made, like it cuts like each of those petals in half.
Right.
So, um, so we're looking at like three halves of all those combined petals.
Yes. So now we can do the same thing but on a smaller scale on the smaller circles. So the by the same notion, this is also equilateral triangle. So we can find the area of this smaller part. The smaller shaded part I have here, we can find the area of that. So we can subtract the area 3 times the area of this from the larger petal we had before, and we can find the area of this. So now let's actually like do it. So let's find the area of this big this big part right here, this thing right here. So we would do 18. So it will be 18 squared pi over 6. That'll be our area of the circle. Area of this circular area right here. Minus 18 squared square root of 3 over 4. And that'll be the area of the equilateral triangle.
So the area of the equilateral triangle, so do you know the formula for the area of an equilateral triangle?
Yes, I do.
So it would be like the side square times root 3 over 4, right? And if you don't know that, you can just derive it.
Yeah,
Or if you
so
also like don't know the formula, you can just like find it by like making like other triangles, right?
right. Yeah, you can just draw a perpendicular from one of the vertices.
Okay.
And this will be 9. This will be 9 square root of 3. And yeah. Okay. So this is the area of this big part right here. Of this part right here. So
Right. And
now,
it's like it's the area of like part of the thing that we're trying to figure out plus like three halves of those petal things.
yes. So now so now we try to find these smaller these parts. So take this, and so to find the area of this, we will have to subtract 3 times the area of this half. So to find the area of this half, so let's do 3 times. In the area of this half, we find it basically the same way we did this first part, which is just this is basically what we did in the first part but on a smaller scale. So we can do 6 squared pi over 6 for the area of the circular region, and then minus 6 squared square root of 3 over 4. And that gets us this part right here. So this ends up being 1/6 of the total area. So now what we can do is we can just multiply this whole thing by 6. So 6 times this whole thing. Whoops. And so because this is the team's composition, you are allowed a calculator. So you kind of just plug this whole thing into a calculator and yeah.
Okay.
Yeah, and it wants nearest whole numbers. So
Yep. So on problems
well,
like this, when the final answer wants to be a nearest whole number, and it involves like pi and stuff, which are like, you know, uh, infinite numbers, you generally want to like keep them in the form of pi until your final calculation. That way, and like not rounding any numbers
but
beforehand.
you mean just like pressing the pi button for pi?
Yeah.
Yeah. Okay.
And also
Yeah.
like when you're doing your work, just keep it expressed as pi until your like final calculation, because that reduces the chance that you might if you round in the middle of your work, that has a chance of your final rounding being off.
Yeah. 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 I mean, generally with like any maths that you do, you want to keep like um everything like as I don't know, as like precise as
Yes.
possible before like you just want to keep everything as precise as possible until you don't have to make it precise, which is like the
Yes.
last step of rounding.
Yes. If you have to round for a
Um,
question, generally you want it to be like the last step. Before that, you want to keep it as precise as possible.
yeah.
Okay,
So
so
you got 11.7.
I got. Oh, my bad. It's percentage. It's my bad. So this is the area of these parts. So now we have to put that over.
Yeah.
We have to put this over the area of the entire circle, which is 18 squared pi. That's my bad. So now we do this.
So yeah, it wants the percent of that area, um
Yeah.
like all of that area over the large circles area. So yeah, Bill found the area of all of that, so now he has to put it over the large squares area to
Right.
get the percentage, and it's
Yeah.
about 12%, and yeah, that's the
Yes.
answer.
And like if you look at the final number ends up being 0.11533 ish. So if you rounded beforehand, that could have very easily tipped the scale and made it 11%, and you would round it down to 11%.
Oh wait, what was the answer? 11 point.
0.11
Oh,
11.53
0 point.
percentage ish.
Oh, okay. Oh, so it's
So
pretty close.
yeah, if you rounded the numbers beforehand, that could have very easily tipped the scale and like made it so
Yeah.
that you would be rounding it to 11% instead of 12%.
Yeah, yeah, you just want to enter in everything as exact as you can. Um, okay, but so it's nearing our end time for today. But for the two problems that we worked today, like what did you feel about them? Like were they easy or were they difficult or what do you think?
Um, I think it was, the problems were a little difficult, um, but overall, I think it was okay.
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 Um.
Well, yeah,
Um,
so
uh,
these problems, or sorry,
uh, uh, um, so I wanted to join the Mathcount Google Classroom, but the code isn't working for me. It's not allowing me to join.
Are you trying to do it on your Lubbock ISD account?
Um, Well, I I think I did, but it still didn't work.
Um, Wait, so are you trying to join with your Lubbock IC email or a different email?
Oh, sorry, 1 second. Yeah, I just checked now. I joined with a different email, not my Lubbock ISD.
Oh, okay. And it didn't work?
No.
Oh, okay.
Wait, so what code are you using?
Uh, ZHJ GQ57.
Yeah,
That's
that's not the code that we have here.
Wait.
Uh,
um
Wait, so where did you get the code that you have?
um I uh my dad he joined a while ago just to look at some stuff, so he had the code there. So it says on the Google Classroom that that was the code, so I put that in, but it didn't work.
Um,
Um,
Wait, Bill, do you have any idea why code might have changed?
no.
Um,
Let's see.
yeah, we do have a different code apparently. I can copy
Oh,
this
yeah,
to you.
like, no, Austin, like,
Yeah,
August 10th here. I can give you a screenshot.
I sent the code in the Google
Okay.
Meet chat,
I
by the
can
way.
give you a screenshot. Yeah. Did we did we make a new classroom or something?
Oh, so this is a really old code. So
Okay.
like, no, yeah, it was something with like